Hi everyone, thank you for joining. Today we're gonna see exploring build caching, practical overview. So first, who am I? I'm Martin Duhem, software engineer. I've been working at Gradle for about 6 months now. I'm working on the velocity for SBT. Prior to that, I was working at Twitter. I was on the IDE team, then the build team, which eventually became the developer experience team when we didn't have enough people to have more teams. Before that, I was working at the Scala Center, on Scala Native, Bloop, Scala Free, and even before that, I was working on SBT and Zinc at Lightbend. So in summary, I've been working on one way or another on comparison build tool for my entire career so far. Today, we're going to first start with seeing what is build caching, and we'll see what is build caching today, what do we have available to us, and continue with what can we do with SBT1X at the moment. So first, to get everyone on the same page with what is build caching, I guess we'll agree that builds take too much time. Very often, they keep repeating exactly the same work over and over again. And if they didn't have to do that, then we would have faster builds. So the goal with build caching is to reuse the partial results of previous builds that we've had. So to put that into more concrete terms, let's imagine that our build is expressed as a collection of proof functions. We have this object build, it defines two functions, compile and test, which compile the sources, run the test. We have some parameters for those build functions. First, we have the sources, list of file, the compiler options, class path, list of file. Produce one jar file, which has the bytecode that we just compiled. For test, it's about the same. We have a test configuration, which would be whether we want to fork, some framework options, and so on, and a class path, which would be, again, the list of jars that we want to run. Produces the test report. And yeah, because we have the function, those build functions, we assume that they are pure. So it means that if we run them twice with the same arguments, we should get the same results. Now, if we define something that will compute a hash for those based on a build function and its arguments, we get a cache key back. That's our hashing function. We can try first, let's call it with the compilation function. We give no sources, no options, no class paths. We get some hash. If we give it some source file, we get different hash, the same for a test, and so on. So using this hash, we can now compute the cache keys and address that against the cache. So we have our object cache, it has function get, take the key, and return us some option of the result. Either we have it in the cache, in this case we get it, or it doesn't, and we have none. We have the cached function, which just wraps one of our build functions and its arguments, compute the hash for that call, tries to get it in the cache. If it's there, good, we return it, otherwise we execute the build function. And basically that's it. That's the idea of build caching. So build caching has benefits. As we've seen, they become faster if they can avoid doing some work, so that's better. If we avoid work, that means that we end up consuming less energy, so we also save money. We have the engineers that don't have to wait around for the builds to finish, so they're more productive, and also they're happier. And eventually, once we have the build caching, it also means that we have the potential to enable more acceleration techniques on top of that. So one of those would be distributed builds, where you have one node that builds the project or some module, and then put the result into the cache, and then the dependent modules that would need to use the result of this previous compilation can just get it from the cache and start building downstream modules in parallel. Test distribution would be about the same concept, where you build once, you put it in the cache, and then you have different test agent executors that would get the bytecode from the cache and execute the test in parallel in different machines without having to rebuild the same project over and over again. So that's all very good, but it's not so easy to implement. Of course, as you can imagine, the example that we've seen at the very beginning, it was much simplified, because there are many things to consider when we want to implement build caching. First, how do we hash a build function? What really does it mean to hash a function? Moreover, we also have to make sure that all the inputs that we give to those functions are machine independent. Because if we start passing absolute paths and so on, it means that we will have the cache key that's going to be different for the same action between machines, so we won't get the cache hits that we would like to have. Another example is that we need to make sure that the build functions that we call upstream from a cache function are stable. So if we, in the result of a function, we have something that's unstable because it includes, for instance, a timestamp, then the cache function is going to have different inputs, so we won't get a cache hit. We also need to make sure that in the function that we want to cache, we capture all the inputs, all the outputs as well, not the effects that are being applied. Because, for instance, if the function that we cache writes some file to disk, but we have no idea about it, then in the second time when we have a cache hit and we don't actually execute the function, then we won't recreate this file on disk, which some dependent function may need. So that would be an issue. So to summarize, it's not easy, especially when we are in an environment that's not controlled. Because we're all Scala developers here, and I guess we're all familiar with incremental compilation, I thought it was interesting to draw some parallels between build caching and incremental compilation. So incremental compilation, we can see it as some kind of very specialized form of build caching. If we take the example of Zinc, Zinc compiles the code and it extracts the symbol, which are the types, classes, values, functions, and so on that you define. And those would be the vertices of the dependency graph that it creates. While it's compiling, it's also analyzing dependencies between those symbols, which end up being the edges of this dependency graph. And when we change a source file and we ask SBT to recompile incrementally, then Zinc is going to compare the source files with the previous ones that it compared, so that only the ones that have been modified are compiled. Then it looks at the individual symbols, and if they haven't changed, like no API change, it means that it doesn't need to recompile the one that depend on those. So that would be the caching. At the bottom, we have a quick comparison between the dependency graph for simplified again for the test task in SBT, so we depend on compile, which depend on update in the sources. The sources need to get them from SBT. It's either managed sources coming from source generators or the unmanaged sources. And on the right, we have an example of dependency graph that Zinc could create for a function called readFile, which would get the lines, which would be a list of string out of a file using source and from file, and so on. So we can see the parallel between the two. Okay, so now that we all on the same page about what is build caching, let's try to see what we have available to us today. So we can't really speak about build caching without mentioning Bazel at some point. So if you're not familiar with Bazel, it has automated support for build caching. It's built in. And one of the reasons why in Bazel it's such an attainable goal to have build caching is because it's artifact-based. What does it mean? Is that all the different build steps that you have, so the different targets and the different things to build in an entire build, they typically consume and produce more artifacts. So you have those different steps. They depend on each other by reusing the artifacts of a previous step. The dependencies between those artifacts are explicitly tracked in the build files of Bazel. Those build files, they usually look like a bunch of function calls, which define the targets that you would like to build. And the way those rules, that we call them, in the build files are implemented is such that the side effects that would be produced by the evaluation of those rules are automatically captured by Bazel. Moreover, the inputs and the outputs of those rules are explicitly declared. So with all this information, Bazel is able, as a rule of thumb, of having build caching work just right out of the box, if we assume that the individual build steps are implemented in a way that the artifacts that we get are stable. So we assume that the compiler, we call it twice with the same inputs, it's going to produce the same thing byte for byte. In SBT1X, we're not quite as lucky. We don't have generalized support out of the box for build caching. And one of the reasons for that is not because of Chrome, is because SBT is task-based. So in SBT, we define the build as a bunch of tasks that are interconnected by dependencies. And generally, tasks they can do anything. It's just a regular thing implemented on the JVM. So it can do anything the JVM can. They can consume anything. They can produce anything. They don't even have to declare that they do. So it's the Wild West for SBT tasks. So all in all, we don't have any API that allows us in SBT to automatically track the actions of a task. So that's why, unfortunately, we can't have generalized and automatic build caching for SBT1X. But that doesn't mean that we can't have any kind of build caching. We can still implement a few things where it makes sense. In SBT2X, the situation should be a bit better. There's been a proposal and an implementation that Eugene came up with that's going to bring cache task in SBT. So the idea is that you would define the task with def.cacheTask, which is a bit different from the def.task that you would use today. If your task is going to declare to produce some file, you can use def.declareOutput to teach SBT about the side effect that you're producing. In this case, writing this file. You don't have to return it. SBT is still going to know that this task produces this file. And that's it. Basically, SBT is going to be able to take care of the rest. It will infer that you depend on the name and version tasks, so that those, if you can reuse, you may skip the evaluation of these tasks and so on. Okay, so we've seen the landscape. So what can we do today in SBT1X? So at the moment, SBT has some specialized support for a few tasks and common operations. One of those is called cache resolution. This is purely local. And the idea is that dependency resolution takes a lot of time because we have to do conflict resolution. So with cache resolution, there is a subgraphs of the entire third-party dependency graph which are taken. And SBT tries to extract subgraphs and cache the conflict resolution that happened for those subgraphs so that it can be reused in next iterations. Different example is incremental compilation that we've discussed. This one is, again, only local and specialized really to the caching of compilation. The last one is called cache compilation. It's remote. We will discuss it a bit more just after. And we also have a bunch of APIs that exist in SBT, but which are not well known, that can be used to implement cache task. First one is cache.cached. It takes as input, like the others, a store, which is really the backing of the cache. So where are we going to write the previous results? It can be used to wrap a function so that consecutive calls to the same function can be reused. So if you call the function twice with the same argument, it's going to be reused. If you call it with a different argument once, then the cache is going to be wiped. File function.cached is very similar, but it writes on functions from a set of file to a set of file. So if you change any of the input files, or if you remove one of those files in the input, it's going to rerun the function. If you also change one of the files that have been produced by the cache function, it's also going to rerun the function so that you get back in the same state. Track the diff inputs and outputs. Those are used to find out about differences in the files that you're passing. So you can see that this file has changed, this file has not changed. You can also configure it with a different style so that you can configure how does SBT decide that a file has changed. Another example is previous that can be called on a task key, which is going to return the result of a previous execution of a task, if it's available. And there are a few more as well. So remote compilation caching. This one is supported by SBT out of the box at the moment. The idea of remote compilation caching is that you kind of package together the class files and the state of the incoming compiler, and you ship it to a remote cache. There are a few tasks that need to be called for that to be used. First one is push remote cache. This one is going to compile, package the state of the incoming compiler along with the class files and put them in the cache. Pull remote cache is going to take the cache state of the incoming compiler and the class files and put them back into place. Remote cache ID is an implementation detail. That is the task that you would use to compute the cache key to address the cache. So it's not very user-friendly at the moment, and also it's not very well known, because we need to remember at each step to repopulate the cache, restore the value from the cache, and so on. But we can do a bit better. So to make it a bit easier to use, we can just use SBT's task graph. So we could redefine the compile task so that compile depends on pull remote cache, and that's it. Whenever we run compile, it's going to fetch from the remote cache before compiling. For push remote cache, it's not quite as simple. Push remote cache, we could try to redefine it so that it's triggered by the evaluation of compile, so that whenever we run compile, it's going to compile and then evaluate push remote cache. That doesn't quite work because if we did this, SBT would try to push after a compilation failure, for instance. And if the compilation went through, then it will also attempt to push to the cache even if it's already populated with that data. So let's see how we can maybe try to come up with a better implementation. So the idea would be that we can have a task, let's call it maybe push, which would push to the cache only if needed. And how can we implement that? The idea is that we can have last push would be the time when it was the last time that we pushed to the cache. The last compilation is the last time that we compiled. And if we've pushed more or as recently as we've compiled, then there is nothing to do. Otherwise, we can just update the cache, re-record that time, and the whole thing is triggered by compile. But how can we implement what's left out? Thankfully, we can use some build caching from SBT to implement it. The first thing that we need to do is to define this as a dynamic task. The reason for that is that we are going to execute this and then execute more tasks based on some condition. So we're not always going to execute the same tasks downstream, so we have to define it as the dynamic task. We need also, the first thing we needed was to know when was the last time that we pushed. So we can use SBT's build caching. Let's have maybe push record the timestamp of the last time that we pushed. So then we can just rely on previous to get the previous evaluation of maybe push, and we are going to get the timestamp when we pushed for last time. Last compilation, this one relies on some other APIs from SBT. The compile task, if you don't know, it produces what's called the analysis, which is basically the output of Zinc, the relation between symbols and so on. But it also has some information about the compilations that happened. We can get the compilations out of this analysis. We get the last one, its start time, and that's it. We have the time of the last compilation. And then, yeah, we fill in the blanks. If we have a push that is as recent as the last compilation, then we don't do anything. If it's older, then we push to the remote cache, and we update the time to be the last compilation. So here, SBT is just automatically going to update the cache after we have newer results, and we can get much easier to use remote compilation caching. So yeah, to summarize this, remote compilation caching, it's based on the same principles that we've seen at the beginning. We gather what matters for a compilation. Those are the inputs that we discussed. We create a cache key out of those. We ask the remote cache for that value. If we find it, we restore it, and that's it. So the key that SBT generates for the remote cache by default, it's based only on the sources, the external dependency class pass. So that would be the list of jars that you are getting from Maven, for instance, and some more internal compiler options. So it's quite coarse because, for instance, it doesn't include the class pass coming from the other modules in your build. So it means that you are going to get more cache hits than you could. But that doesn't really matter in our case because SBT is still going to call Zinc after restoring the incremental compiler state, so that if your class pass has changed, Zinc is going to run, detect that you need to recompile some source files, recompile what's needed, and get back into a clean state. And finally, if you need, that's SBT, so everything's configurable. You can just override the remote cache ID task so that you get a finer grained cache key. Second example of build caching would be a build function where we would like to check the licenses that we have in our third-party dependencies. So first we have a collect licenses task, which looks at the external dependency class pass, a list of jars coming from external dependencies. It extracts it, look at the license files, and then we have check licenses, which get those license files, verify whether those are GPL, and if we have any GPL license on the class pass, then just return an error. Because that's a check that we would like to do quite often, we override the test task in SBT so that it depends on this check licenses task. So whenever we run the test, then we run the check licenses. Unfortunately, that means that whenever we run the test, we're going to extract all of those jars from the class path, which can take quite a bit of time. And we're redoing the same work over and over again. So what would it look like if we were to improve it a bit with build caching? We have those APIs that exist in SBT. This is the file function that we are going to use here. This one works on the input and output files. So we have the input files that we get here. We can have checked, which is the list of files that SBT tracks. And we extract those, get the licenses just like before. So as long as the class path doesn't change, it's not going to be re-executed. It's going to reuse the same values from before. So that's it. That's about how hard it becomes to implement a new cache task out of a non-cache task in SBT. Yeah, it becomes a no-op as long as you don't change the class path. You can save some time. So this is applicable to many common tasks in SBT. So for instance, sources and resources generation, which take time. You can just track the output, like the sources and resources that you generate. If you don't have other inputs, it is not going to change as long as you don't delete those on the disk, for instance. You can use this for verification, just like the example we've seen. You could use this for archiving, for instance. If you are building an Uber jar from more jars, then you may not want to rebuild it if your class path or input jars haven't changed. Same goes for shading. If you have the same shading rules, you don't want to rebuild this shaded jar, and so on. Those APIs that we've seen, we've discussed quickly about the store that they take, which is the backing of the cache. It's a very generic API that you could just re-implement so that it's either local or remote. But unfortunately, doing those changes requires you to know about the task implementation so that you can modify it and actually do the changes. And finally, you also need to identify which are the tasks that are worth caching. If you've seen Julian's presentation earlier today, maybe you got a few ideas on how to do this. Another example is the caching of test execution results. So if we were to implement that, we would go back to the first principles that we had. And so let's try to see what it would take to cache the test execution results. So we can go in SBT. Defaults.scala is basically the file in SBT that has all the default task implementations. We can look at it and find how our tests executed. So it's easy to identify the list of dependencies of this task that you can see here. But that would be the inputs of test execution. So if we have the inputs, we can compute a cache key out of those. So let's define a test cache key that has 4 fields, those inputs that we've defined, and we can redefine the execute test task. So again, it's going to be a dynamic task, just like before, because we're either going to execute a task that does nothing if we have a cache hit, or we're going to execute another task if it's a cache miss. So we have the actual task, which is the work to do. We don't execute it at this point. We create the cache key. We initiate some store to store the result of test execution or get it back from. We have the cache. Ask the cache for the cache key that we just defined. In case of a hit, we have nothing to do. If it's a miss, we have the update function, and we can execute the actual task, and with the result, we put it in the cache and return the result. So it's quite easy. It looks like a framework that we could reuse. So can we actually generalize? But we've seen how to manually collect the task input. We've seen how to manually refactor the task, but that's a lot of work, and we still have to decide what to do. But hopefully we can define some kind of helper function that will help us rewrite those cache tasks in a way that would be more easy. So that's why its interface could look like. So we'll have cache task that produces some type T. We need some JSON format to write this task to write the result to disk. That's just an implementation detail from SBT that is going to define how we serialize the type that is generated by the cache. We have again the actual task. The cache key, we have to figure out how to compute it. The store, that's like before, and the rest just the same. But we still have those questions. Where is this implicit JSON format going to come from? How do we compute this cache key? SBT has this task graph that I'm sure you're familiar with. And SBT knows ahead of time what tasks are going to be executed when you execute a normal task. With dynamic task, it's a bit different because the tasks to be executed are going to be chosen at runtime based on some condition. But if we assume only that we're working on non-dynamic task, we can gather the dependencies from the build structure. So this is something that's available to us in SBT. You can look in the state, you can get the structure. So that's how we can get the inputs of the task. We still need to get the outputs of the dependent tasks so that we can hash them, see whether we've seen those before, and ask in the cache. We can get those through SBT's task progress listener. So that's a callback that gets called whenever a task finishes. We have the task key along with the result. So we can get the inputs, we can get the outputs of those tasks. We still need to hash them into cache key in a way, one way or another. So yeah, we still need to figure out how to serialize also the result of the task in the end so that it can be written to the cache. So there are still those open questions. How do we hash the input values into a cache key? How do we account also for the task implementation to the cache key? Because if we were to change the task implementation slightly, we need to invalidate the previous runs so that we don't return a result that was produced by the previous implementation of the task, of course. And finally, we need to serialize the task result. Unfortunately, those are still kind of open, but that's what we're working on. So to conclude, we have a variety of functions that can be used in SBT to cache the results of the build. All of those functions at the moment, they can completely work with a remote cache. You have to implement a cache store that would communicate with a remote machine. But yeah, using those functions that exist at the moment, you really need knowledge of the task implementation. You need to figure which tasks need to be cached so that your build can benefit from the most acceleration. We can try to generalize, and we can get a bit of that information out of SBT's task graph, but we still need to figure out how to hash the inputs, how to serialize the outputs, and this is what we're currently working on at Gradle. And finally, dynamic tasks, they remain black boxes. Yep, that's all I had. Thank you.